All right, good morning. This is day 36. We're starting chapter 6 and 16. And these are notes you should be watching. I'm not doing them in class, but you need to watch them and fill in your notes as we go. This is not going to be done in class, so you need to watch this. So day 36, we're starting on the normal model, and this is what we'll use for the rest of the year. This is so important. We'll spend about 3 days just going over how to use the normal model. So when distributions are unimodal and symmetric, here's an example of a dot plot that would be unimodal and symmetric. Basically, a unimodal and symmetric dot plot is basically one that looks kind of like a mountain, a hill. Okay, you've got typically, and mine's kind of just crazy everywhere. It would be nice and straight, but it's kind of mound-shaped as unimodal and symmetric. Usually the highest point is somewhere in the middle. It might be slightly off to the side, and then you've got lower things on each end. And the normal curve, this is a distribution that would be unimodal and symmetric, and the normal distribution looks somewhat like this. Mine's not going to be perfect here, but this is the normal distribution. It's actually down just slightly farther on your page. So a normal curve. This is the normal curve. And this is the curve, like when people say, hey, you want to curve your grades, this is the curve that they are typically referring to. So technically, the normal curve is a mathematical function, and it involves the number e, that extends from negative infinity to positive infinity. Thus, a normal curve will never model a data set perfectly. Never model a data set perfectly. Because we never have a data set that, like if there's 100 in it, this goes on for infinity. This curve technically never ever touches the x-axis. So it kind of just glides above the x-axis, and it never goes below the x-axis. So this curve can't truly exactly model data. So we never say we have normal data. We always say we have approximately normal. Approximately normal. Who's normal anyways, right? Okay, and data set should be described as approximately normal, never normal. When we use mathematical function to describe a distribution of real data, we call the function a model. Just like we had a model for linear regression, we had the least squares regression line, which was a model for our ordered pairs that we had. Our ordered pairs and made a scatter plot, and that was too random. We didn't like that. So we made a mathematical model and fit those to a line. So a normal curve is also a model for distributions that are unimodal and symmetric. In the normal model, it is centered around the mean mu and a standard deviation of sigma. This is mu, the Greek letter mu, and that is the Greek letter sigma. So a normal distribution, the way we write a normal distribution is capital N, begin parentheses, mu, comma, sigma. And sometimes if you're dealing with data, it's x bar, comma, s. So x bar is the sample, if you've taken a sample mean, and s is the sample standard deviation. These are the census or true values. True values, sample. All right, when graphing a normal distribution, the inflection points, well, if you don't know what inflection points, they're points where a graph changes from concave up to concave down. So they're located at one standard deviation above and below the mean. An inflection point is where a graph goes from concave up, happy face, to concave down, frowny face. So this is what a normal distribution looks like. So basically, here is always in the middle, here's your x-axis. Always in the middle is the mean, that's mu, right in the middle. Okay, the first mark above is +1 standard deviation, 1 sigma. The second mark is +2 sigma, and the third mark is the third standard deviation. And if you go the other way, it's 1 standard deviation below, -2 standard deviations below the mean, and 3 standard deviations below the mean. So these marks represent a standard deviation below the mean. So it says that from here at the 1 standard deviation to draw a normal curve, basically you're just going to, here's the concave up or concave down, and then these other parts are concave up, and it happens at the first standard deviation. We use Greek letters to denote that these values are not calculated from data in a sample. They are either calculated from entire populations or they are assumed values to help us solve problems to start with. Numbers like these are called parameters. For example, mu and sigma. In contrast, summaries of data from samples are called statistics. That's what we calculate. We calculate statistics. Parameters are true values that we believe maybe we gathered from a census. They're represented with non-Greek letters that we talked about up here, X bar and S. So now we have this rule. This is the key rule here for the normal curve. Very, very, very important. It's called the 68, 95, 99.7 rule. Basically the 68%, the 95%, the 99.7% rule. When a distribution is approximately normal, then approximately 68% of the observations will be within one standard deviation. So in this little box right here, there will be 68% of all observations. That leaves 34% in the standard deviation above the mean and 34% in the standard deviation below the mean. Okay, one standard deviation above the mean, that's 68%. 95% of the observations will be within two standard deviations. So if I took this entire area that I'm putting this box around here and colored it in, that box would represent 95% of all of the data that I've collected or that we have. So if 95% takes up this whole thing, and that's two standard deviations, that means like half of 95, so that's 47.5% over below and 47.5% above are within two standard deviations. And then if I make a whole big box around all three standard deviations, everything inside that entire big box represents 99.7% of all data. So above the mean, the data that will be above the mean, three standard deviations, if you take 99.7 divided by 2, that gives you about 49.85% and 49.85% above and below three standard deviations. So pretty much what you have to realize here is that almost all of your data is within three standard deviations. Only 0.3% of data outside plus and minus three standard deviations. Only 0.3% of your data for a normal curve. All right, so note how to draw a normal curve. Start with the axis and label the mean and three standard deviations in each direction. So start with the x-axis and label the mean, mu, and 1, 2, 3, 1 sigma, 2 sigma, 3 sigma, and 1, 2, 3, negative 1 sigma, negative 2 sigma, negative 3 sigma. Okay, that's how you put the x-axis. And then place a dot above the mean for the curve, so just put a dot somewhere up here. Place dots at 60% of this height, so here's 50, here's 60% of that height. For the first standard deviation, draw it concave down. And then place dots at 1/8 of this height for two standard deviations, so there's a half, a fourth, an eighth of that height for two standard deviations. And then I basically draw it concave up, not ever touching the x-axis. So these are instructions on how to draw a normal curve, because you'll be drawing lots and lots and lots of them. Learn to love it. It's wonderful. It will be your friend. All right, so now we're on the next page. So now we're going to just talk about, suppose the birth weights of newborn babies are approximately normal with a mean of 7.6 pounds and a standard deviation of 1.3 pounds. Sketch the normal curve with the correct scale. So this is your job on pretty much every problem to start with. If we are going to assume it's normal, is you are going to draw the normal model. And so we're going to draw another one right here. So here's our mean. And there's 1, 2, 3 standard deviations, 2 sigma, 3 sigma, minus 1 sigma, minus 2 sigma, minus 3 sigma. Put a dot here, halfway, a little bit above. Draw your concave down, halfway down, 1/8 of the way for the second. There's our normal curve. Now, what we want to do, actually, instead of this -3 standard deviation, -2 standard deviation, -1, we actually want to replace all of those with numbers from our situation. So instead of drawing those, we just need to put the marks the next time. So when I draw this actual normal curve, I'm just going to put 1, 2, 3, and I typically just draw this big line up here. That way I can tell that that is the mean. I just put a dot somewhere up here, mark the halfway, go a little above for one standard deviation, go halfway, 1/8, halfway, well, 1/4 and 1/8 for the second standard deviation, and draw my normal curve. Okay, so now what I want to label here, the mean is 1.3 pounds, so I'm going to put 1.3 pounds. And then I want to label each of the standard deviations. So, sorry, whoops, that's wrong. It's not a mean of 1.3, it's a mean of 7.6 pounds. And then the standard deviation is 1.3 pounds. But I don't just put 1.3, 1.3, 1.3. I have to add 1.3 to 7.6 3 times to get the different standard deviations. So I'm just going to take 7.6 plus 1.3, and that gives me that the first standard deviation is 8.9 pounds. And we're going to use this for all the questions that we have to answer. And then I'm just going to add 1.3 again, and that's going to give me that this mark would be 10.2 pounds. And then I'm going to add 1.3 again, and that's going to give me that this mark will be 11.5 pounds. Okay, now I'm going to go back to the 7.6, and now I'm going to get the other standard deviations by subtracting 1.3, and that gives me that this is 6.3 pounds. And then subtract 1.3 again, that gives me that this one is 5 pounds. And then subtract 1.3 again, and that gives me that this is 3.7 pounds. So this is the normal distribution for the birth weights of newborn babies, and it says what percentage of babies, what percentage, this is kind of like a probability, what's a probability that a baby will weigh less than 8.9 pounds, what percentage of babies will weigh less than 8.9 pounds? Okay, so we just go here and we will see that 8.9 pounds happens to go exactly with that standard deviation right there. So now here's where we're going to use our rule that we just had on the other page. Okay, so what I know is that in this little thing, 68% of all the data. Within this bigger thing, that's going to be 95% of all the data. And within this is 99.7% of all of the data. So I need to figure out basically what percent is over here. So for this particular problem, what percentage of babies will weigh that? Here's how you need to get used to. You need to get used to drawing lots of normal curves, okay? Because basically to show this is you're basically shading areas under a curve. So if we want to know the percent of babies that will weigh less than 8.9 pounds, I look on my x-axis, here's 8.9, everything less than it is over here. So if I go down here, this is where the 8.9 was, everything less than it is over here. If you think of, if you shade under the entire normal curve, you've shaded 100%, okay? If you only shade a portion of it, you've only shaded some percent. Now using this thing here, we can figure out what percent. Because I'm at the one standard deviation mark right here. Okay, so now I can't just use these values here. I know that the whole thing would be 100%. Okay, I know basically, here's how easy this is. If the whole thing is 100%, what percent's below the mean? 50% below the mean and 50% above the mean. Okay, so basically if I have this, if I just have this half of my normal distribution shaded, I automatically have 50%. And if I utilize this and know I've shaded one standard deviation above that now, that if I shaded one standard deviation above and below, that would be 68, but since I'm just taking half of that, I take half of 68, so this is 34%. So if I add those two together, that means I have 84% of babies will weigh less than 8.9 pounds. Okay, what percentage will weigh more than 8.9 pounds? Well, that's just the other part of it. All we're doing for this part, for part 3, is we're shading up here. Well, if the whole thing has to add up to 100, we just take 1 minus 84%, and that's just going to give us 16% of babies. All right, what percentage will weigh more than 5 pounds? Okay, well, more than 5 pounds. 5 pounds does happen to be value on our thing too. It happens to be right here, 2 standard deviations below the mean. So 1, 2. So I need to shade everything above that. I'll finish this up on the next video.